Hi, I'm Connor Aparicio-Bill, and I'm going to be talking about applying circuit analysis to solar energy, designing a photovoltaic system for Kealakehe High School. My faculty advisor is Dr. Hanai. The Big Island of Hawaii receives strong and consistent sunlight throughout the year, making solar energy a practical way to reduce electricity use from fossil fuels while supporting long-term sustainability. This project focuses on improving energy use at Kealakehe High School by exploring a conceptual solar panel designed for one of the main campus buildings. The engineering problem addressed in this project is how to design a solar panel system that can supply useful electrical energy to the building while maintaining reliable voltage delivery based on the school's electrical needs. Key design parameters include the available roof area, expected solar exposure, electrical power demand of the building, and the arrangement of solar panels within the system. The electrical behavior of the solar panel system can be analyzed using concepts learned in a community college circuit analysis course. In particular, Thevenin's theorem allows a complex electrical network to be simplified into an equivalent circuit consisting of a single voltage source in series with an equivalent resistor. This simplified model makes it easier to understand how the solar array supplies power to the building and how the voltage delivered to the load changes as electrical demand varies. Using this voltage source and series resistance model, the solar panel system can be represented with a Thevenin equivalent circuit to estimate how power is transferred to the building. This approach connects theoretical circuit analysis to concepts to a practical engineering application while demonstrating how solar panel energy can support sustainability on a school campus. To address the challenge of providing reliable solar panel to Q building at Kealakehe High School, a solar panel system was designed to maximize energy production while fitting the available roof space. The prototype includes a conceptual layout of the photovoltaic panels, positioned to capture the most sunlight throughout the year, and planned connection to the building's electrical system. The system was modeled as a Thevenin equivalent circuit, representing the solar array as a voltage source in series with a resistor. This allowed the analysis of voltage, current, and power delivery under different load conditions. The design process was iterative, guided by both practical and analytical considerations. Early designs aimed to cover as much roof area as possible, but later iterations adjusted the panel layout to account for shading, roof orientation, and the building's actual power needs. Each version was analyzed using Aladdin to estimate annual energy production and system costs. This information guided decisions on the number of panels, their arrangement, and the expected performance of the system. After multiple iterations, the final design balances energy output, cost, and efficiency. The prototype demonstrates a feasible solar panel system for Q building that could meet the building's electrical needs, support sustainability goals, and provide a practical example of applying circuit analysis concepts like Thevenin's equivalence in real-world engineering design. In Figure 1, you can see the final design for the solar panel layout for Kealakehe High School's Q building with the energy generation shown on the right. Using the analysis tools provided in ALID, yearly solar analysis yield was performed after each iteration of the design. For each prototype version, the software was used to estimate the total annual energy production of the solar panels as well as the overall cost of installing the system. This allowed the design to be evaluated based on both its energy output and economic feasibility. The results of each analysis were then used to determine whether the design was successful. A design was considered successful if the system generated enough energy to fulfill the building's needs or more than necessary. In either case, this indicated that the solar panels were producing enough electrical energy to justify the cost of their implementation. By repeating this process after each design revision, the solar panel layout and system configuration could be refined to improve both performance and cost effectiveness. As you can see in Figure 2, the total solar energy generation from the cumulative solar panel design is shown. Based on the prototype results, the proposed solar panel system for Kealakehe High School demonstrates promising energy generation, but targeted improvements are needed to enhance efficiency and cost reduction in the next design iteration. Future work will focus on optimizing panel placements to reduce shading, refining panel orientation to maximize solar exposure, and improving the electrical configuration to minimize losses and better match the building's load demands. These refinements will be supported by continued application of circuit analysis concepts, particularly the use of Thevenin's theorem, to accurately model system behavior and update equivalent circuit parameters based on observed performance. This project is significant because it demonstrates how circuit modeling serves as a critical bridge between theoretical analysis and real-world engineering design, enabling complex renewable energy systems to be simplified, analyzed, and optimized. Similar modeling approaches are widely used in solar energy research to predict performance and guide system improvements, highlighting how foundational circuit analysis techniques play a key role in developing efficient, cost-effective, and sustainable energy solutions. Thank you.